So here's our next problem we're going to be taking a look at. So we have a 4-bar mechanism. All right, we've seen a couple 4-bar things around. And we know here's the input side. So angular velocity is 1 radian per second, and it's accelerating at half a radian per second squared. This is basically a parallelogram system. So both these sides and also this distance and that distance across are all this and that are equal, that and that are equal. So what we have here is a parallelogram. So just taking different shapes as it rotates through. And if we look at the parallelogram, we see there's this box, 50 kilogram crate. The coefficient of static friction from the crate to this rod is 0.5. It's given up here. And the question is the crate sitting still relative to this crossbar? Or is it tipping and slipping? All right. Well, if it is sitting still, we know a lot. So let's think about this. We can, knowing this is 0 and then knowing the alpha, omega and alpha, we can determine the acceleration right there. And in fact, you'll have the same acceleration all along this bar, because whatever this is doing, it's a parallelogram, this side is doing. So each of these endpoints are doing the same thing. Therefore, everything attached to the body or sitting on the body, if it's sitting still, is doing the exact same thing. So we have a box, it's 1.5 meters by 0.5 meter. And so what we want to do is simply compute the acceleration here, because we can. Then we'll know the acceleration everywhere, and so what we need to do then is sum the forces and moments in an appropriate way on this box to see if it can handle the accelerations that we find right here. If not, then we'll start figuring out how it's moving. So the first question is how is this point accelerating, which will be the same as that point if it's not moving. So here I have AGC, assuming that it's not moving. So I just have alpha cross r down to here, minus omega squared r. And if you go through the math, if this thing is not moving, then the acceleration of the center of mass for this box is given by the following. All right? So knowing that, here's our free body diagram. Very straightforward. So here's the box. Here's the weight, 50 times g. If it's sitting still, then the system is generally going like this, so friction is moving it along. All right? So we have the normal force, and the maximum friction force that would be available would be the normal force times, moving this down slightly, US, which is 0.5. So what we want to do is figure out, is there enough friction force? And then based on the friction force, how far out is this normal going to see if we have enough width here to support it. If normal force winds up outside the body, then we know where we'd be tipping. All right. So summing the forces. So that's what we'll do first. The only external force in the X is friction. All right. And we know, so I call that Fc. You see there's Fc right there. Equals mass times acceleration, which we get up here. The acceleration mass is 50 kilograms. If I multiply those together, it's 186.6. All right. So the question is can we get 186.6 newtons due to friction here? Well, to determine that, we need to determine what the normal force is. Well, that's just summing the y. So that's right here. So we have a normal force coming up minus 50 times g equals, and it's not 0. It'll be very easy on an exam for I could just see students say, oh, the normal force is equal to that. No. The center of mass is actually, for this box, is accelerating. We have it right there. That's what we already determined. Okay, so it's n minus 50g equals mass 50 times acceleration in the y of the center of mass. Solve for n. we get 613.7 newtons. And if you take half of that, right here, that's 300, basically 307 newtons, which is much bigger than the 186 we calculated here. So there's basically a friction force available of 307 newtons, but we only need this much of it. So it's readily available. We have no trouble having this sit in place due to friction. Okay, so now we know what friction is. From solving this, we know, okay, friction is roughly 187 newtons. And as we say here, it won't slide. The question is yeah, it won't slide, but where's that normal force? Is it still within the box? All right, well, that's where we go, and we'll assume that it's not tipping. So we'll take the sum of the moments at G, right up in here. So that would be FC times 0.75 to get to G. It's counterclockwise, that's positive. Minus N times X, that would be a clockwise, that's why it's negative, equals 0. Solve for X. Come up with 0.228 meters, which is less than 0.25, because this is overall width was 0.5 meters up here. There's that. So 0.228, it's less than 0.25, not a problem, it's not tipping. So the question was, is this thing not sliding, not tipping? Is it staying with the bar? Is it still relative to the bar? Yes, it is. So we have that problem. All right. We're going to be doing 3 more problems. And all of these problems, basically, that I'm going to be doing next have issues relative to getting enough equations. So you have to appeal to kinematics, and then once you get enough equations, so the number of equations and knowns is equal, then it's just an algebraic exercise. So I will be showing you 3 more problems now where the focus is just getting all the equations. We'll see you then.